Hello everyone, my name is Leon Müller, and with this presentation we present an aircraft marshalling signals dataset from FMCW radar and an event-based camera for exploring sensor fusion and efficient encodings. This work is a collaboration between Stichting IMEC in Eindhoven, the Netherlands, as well as the Eindhoven University of Technology. Before we go into the details, we want to give a small sneak peek into the dataset and the motivation for publishing. We collected aircraft marshalling signals, which are full-body gestures, using two modalities, a DVS or dynamic vision sensor, which can be seen on the left of the animation, as well as a FMCW radar sensor, whose raw ADC data can be seen on the right. We saw the need for this dataset for a couple of reasons. First, we wanted to provide more content than comparable datasets, meaning more distances from the sensor, more environments, and also more subjects. Next, by providing two modalities, we enable the comparison and also exploration of sensor fusion. The radar we have used is very low power and relatively low resolution, which also makes the dataset more challenging. Finally, in contrast to related datasets, we provide the raw data inputs from both the DVS and the radar, enabling the exploration of different input representations and encodings. This presentation is roughly divided into three parts. First, we give a small introduction into the advantage of radar processing with neural networks and the importance of pre-processing at the sensor end. Next, we introduce our dataset and the sensor modalities in greater detail. And finally, we show first validation experiments with our dataset, namely a highly memory-efficient radar encoding, as well as the advantage of doing sensor fusion. While traditional radar processing has been around for a while, several interesting and novel applications have been enabled by utilizing neural networks to process radar data. Many publications focus on gesture classification for commands, with one noteworthy example being the Google Solly paper by Lien et al., which presents a system for small gestures performed in front of a miniature radar sensor to control, for example, volume or skip songs. A similar example shows a CNN capable of classifying handwriting in air captured by two radar sensors. Other examples include altitude control and ranging for autonomous vehicles, person identification based on gait, object detection in autonomous driving, as well as non-contact vital sign detection. Finally, as radar is largely unaffected by occlusion and poor lighting conditions, it's also an interesting alternative or supporting modality for traditional camera-based applications which can suffer from occlusion and poor lighting conditions. We just gave a couple of examples where neural networks extend the application coverage of typical radar sensor applications. Another benefit of utilizing neural networks for radar processing is that it enables a more natural and flexible way of performing sensor fusion with other modalities. For example, through early fusion, where the input channels of a CNN are set to the different modalities. However, when you want to employ more efficient and sparse networks, we might also want to look at processing data directly at the sensor end to reduce the data bandwidth from the sensor. In the case of a stationary radar and classification of movement in front of the radar, a majority of the transmitted data contains only the background and is thus redundant. Not transmitting the static parts of the radar data, this enables us a drastic reduction of data volume and communication requirements, and furthermore enables the usage of event-based processing, for example with spiky neural networks. By providing raw data straight from the sensor instead of already pre-processed data, our dataset also enables the exploration on the most efficient encodings for radar data and potential pre-processing methods to be integrated into the sensor end. To further motivate the publication of our dataset, we looked at related datasets which also feature gesture data. From this review, we conclude that current datasets lack a number of important and desirable features. First, they mainly focus on small hand-based gestures instead of full-body gestures, and thus tend to require higher resolution and higher power radar. Next, none of the datasets provide raw ADC data, making it hard to explore different input representations and efficient encodings which could be provided by on-sensor pre-processing. Our dataset is also the first dataset to provide multimodality for full-body gestures, which allows to compare the different modalities and enables the exploration of sensor fusion. We also provide a higher number of environments to allow a trained network to better generalize to multiple and potentially unknown environments and subjects. Finally, we provide a challenging set of validation data which includes unseen subjects and environments, which allows to better quantize the real-world performance of such an application. We now take a closer look at the dataset in more detail. I will first explain the different modalities that are present in our dataset, how they've been synchronized, and then finally I'll give a detailed description of the gestures that are part of our dataset. One of the modalities present in our dataset is an 8 GHz ultra-wideband FMCW radar sensor with a single input, single output antenna, which has been developed by IMEC. It is aimed to be low power, with under a milliwatt of power needed during capture. The frequency modulated constant wave radar, or also FMCW radar for short, can estimate the distances of objects in front of the radar with a range resolution of around 15 centimeters. For this, a one-dimensional Fourier transform across each strip must be performed. An example can be seen in the highlighted figure, which shows the presence of objects in a subset of range bands over time. This is also known as a range map. The radar can also estimate the velocity of objects moving during a frame. In a frame, for example, can be 192 chirps, which would be roughly 250 milliseconds. Velocity estimation makes use of the Doppler shift in the return frequency. After performing a two-dimensional Fourier transform, once across the single chirps to get the range, and then across all chirps in the frame to get velocity, we get a Doppler map showing the velocity of objects across the different frequency bands and distances, which can be seen in the lower right of the slide. The other modality present in the dataset is a dynamic vision sensor from IniLabs. A dynamic vision sensor, or DVS for short, can also be known as a neuromorphic vision sensor or an event-based camera. And it is a type of image sensor that operates differently from traditional cameras. As such, DVS cameras only report changes in the scene, capturing a stream of events that represent light intensity changes at specific pixels. An example from our dataset can be seen in the bottom right, which shows the events that are generated as the person moves their arms during performing of a gesture. DVS cameras have several advantages over traditional cameras. For one, they offer a higher speed, which is a few microsecond pixel latencies. Second, they are more energy efficient as they reduce the amount of redundant data that is transmitted. And three, they offer high dynamic range as the pixel array does not require equal exposure times, but all pixels work independently of one to another. The two modalities in our dataset have been synchronized at millisecond resolution using hardware signaling by feeding the rising edge of the radar's pulse repetition interval, PRI, which indicates the start of a chirp, directly to the DVS camera, which in turn generates a special event in the event stream of the DVS, which we can pick up. This enables timestamping and enumerating the radar chirps using the DVS's camera's clock and aligning individual radar chirp transmissions with a corresponding set of polarity events generated during that chirp by the DVS camera. We perform 10 aircraft marshaling signals in front of our platform, which are full-body gestures involving hand and arm movement. Two example gestures can be seen playing in the bottom right, as they have been captured by the DVS camera. Our training set contains two spaces, namely a conference room and a foyer, with 6 unique subjects who have performed the 10 gestures at 6 distinct distances, ranging from 1.5 meters to 4.5 meters in 0.5 meters increments. Furthermore, the subjects also face the radar at different angles. A separate validation set contains an additional 7 unseen subjects, as well as a third unseen environment, an open space, where subjects also face the radar at different distances and angles. In addition to the 10 gestures, we also recorded a collection of samples with no gesture performed. These captures show either empty rooms with no people in it, or subjects standing still or walking around while performing no gestures. Finally, and most importantly, we also provide the raw ADC data from the radar and the raw event stream from the DVS. In this slide, we can see a quick overview of all the gestures that are included in our dataset and how they have been performed in front of the camera. To validate the usefulness of our dataset, we explored two areas of interest. First, using the raw ADC radar data, we developed a highly memory-efficient radar data encoding specifically for neural network processing. And second, we created baselines using neural networks, showing that sensor fusion of the two modalities enables us to gain better classification accuracy than each modality alone does. Let's first take a look at the sparse binary radar encoding we have engineered using the raw ADC data available on our dataset. As previously mentioned, the raw radar data contains a lot of redundant information, namely the static background that is reflected with each chirp. As we're only interested in movement, we propose to filter this data out via two operations, a delta operation and a binarization and thresholding operation. For the first order delta filter, we simply subtract successive chirps from one another, which means that the unchanged values across chirps are simply set to 0. Next, we apply a binarization operation on the delta data by applying a level crossing operation with a threshold alpha. Every change below the threshold alpha is set to 0, and everything above it is set to either +1 or -1 depending on the sign of the delta. The delta operation high-pass filters the data, removing static objects, and the thresholding operation removes unwanted noise. The binarization operation allows us to greatly reduce the data width as well, potentially only requiring 1 bit to represent positive and negative events. In the top of the figure on the right, we can see the raw ADC data on the left and the ADC data after applying the delta and binarization operation on the right. We can clearly see that the static parts, which stay the same during successive chirps, is removed. In our dataset, 73% of data was set to 0 after this operation on average. The operation is also easy to implement on the sensor end, as it only requires a buffer of a single chirp to subtract with. If you now compare the resulting Doppler map of the raw ADC data on the left and the delta processed and binarized data on the right, we can see that the frequency information has been retained and the same velocity information is still present in both graphs. We found that the threshold alpha equal to the standard deviation within a capture is a good balance between retaining accuracy and reduced data density. For this, we tried different values for a threshold alpha, which we can see on the x-axis of the graph. The number above the threshold shows the resulting density of the data, so non-zero values, when this threshold is applied. On the y-axis, we can see the classification accuracy for a baseline neural network trained on gesture classification using only Doppler maps from the radar. In the graph, we can see that for a threshold lower than a standard deviation, density is increased while giving no real benefit in accuracy. However, if we go above the standard deviation, we can quickly see a further decrease in density. However, this also seems to greatly impact the classification accuracy. As such, an alpha equal to the standard deviation seems to bring the best balance between retaining accuracy and sparsifying the data. The standard deviation seems to be largely the same for captures in the same environment and slightly varies with different environments. With a threshold at the standard deviation, we can also see that accuracy is only minimally affected, within 2% plus or minus, while we are able to reduce the density of the raw ADC data by an average of around 73%. For our second validation experiment, we also wanted to validate if and how sensor fusion of the DVS camera events and the radar Doppler maps can lead to better gesture classification accuracy. For a baseline, we fine-tuned pre-trained networks, namely Resonant 18 and EfficientNet B1, with 3 different input configurations. For the first, we provided 3 times the same Doppler map from the radar. For the DVS only, we provided a 2D frame resulting from the aggregation of negative and positive events replicated on the 3 input channels. And for an early fusion approach, where we set the 2 channels to the negative and positive event frames of the DVS and the last channel to the Doppler map from the radar. As we can see on the table below, radar performs by itself worse than the DVS does. But this is to be expected due to the low resolution of the radar, and thus some of the gestures can look very similar to the radar. If we only take the best 5 gestures, we can see a much better accuracy, which shows that the dataset is sufficiently challenging. We can also see that the accuracy is improved when fusing both modalities, which confirms that the information given to the model from each modality is partially orthogonal to the other and that they complement each other well. Note that these results are just baselines for initial validation, and more custom-tailored neural networks are going to give much better results. Finally, a part of the testing set has been collected during a live demonstration of the system in an unknown environment, with unknown subjects at multiple angles and distances from the radar. With a model based on EfficientNet B1, trained on fused DVS and radar data, we were able to achieve an accuracy of 95.53%, which is a very good performance considering that the system was placed in a completely novel environment and used by subjects that are unknown to the network. Due to the efficient nature of EfficientNet, computation was also very quick on a completely non-accelerated laptop. In conclusion, first, we have explained why processing radar data with neural networks is desirable and the advantages it can bring in terms of sensor fusion. Next, we motivated the creation of our dataset and outlined how it improves upon currently existing datasets, namely by providing more diversity in subjects and environments, and by providing multimodal and raw data, which allows for the exploration on efficient encodings and sensor fusion. And finally, we have validated the usefulness of our dataset by engineering a memory-efficient radar encoding, which reduces the density of raw ADC data by 70% on average, and showing that multimodal sensor fusion can lead to increased classification accuracy. Finally, we hope that this dataset will enable future research into more efficient encodings for radar data and enable on-sensor processing, as well as sensor fusion. Due to the event-based nature of our DVS camera and proposed encoding, we also hope to see this dataset to be utilized for benchmarking event-based systems, namely through neuromorphic processing and spiking neural networks. Thanks very much for your attention. My name is Leon Müller, but I'd also like to thank all the people that have been involved in the creation of this publication, both from IMEC and the Eindhoven University of Technology. You can access the dataset by searching for the DOI shown here or by clicking the link in the presentation. Thank you very much and have a nice day.